transforms. Linearity, important property. Sometimes that sounds a bit like the cat chasing its tail. And what it says, if you put an input x of n, and so our system is some kind of transfer function. We haven't said whether it's linear or time invariant, so we just call it t. So whatever the transformation is of x of n, we call the output y of n. So I put in x1. If I view this as an experiment, I put in x1, and whatever I measure at the output, I call y1. Similarly, I put in some sequence x2, whatever comes out, I call that y2. So I do another experiment and call the output y2 of n, just dropping the n's here. Now, if I put an input that is a x1 plus b y1, bx2, in that case, the output has to be a y1 plus b y2 for the final experiment if the system is linear. So the best way to envision this rule is just do 3 experiments, and the output should be a times the original measured output plus b times the second measured output when the input to the system is a times the first input plus b times the second. One simple test would be to just do a simple test. One property we can see here, ignoring y2, is that if I put in 2 times x1, then that would say I would get 2 times whatever the original output is. And so a simple example that violates that case is a squaring box. And so if you had a box that was just squared what the input is, if I put 1s in, I get out 1, but if I put 2 in, I get out 4. And so that box is clearly nonlinear because when I double the input, I get 4 times the output. A simple example or word statement of a linear is if I wrap the top of a desk with my knuckles, it makes a sound. If I do it twice as hard, I expect the sound to be twice as loud. That's just a simple kind of word statement of what you expect with a linear system. Time invariance, the mathematical statement is that if the output for an input is called y of n, then if I shift the input by some n sub d, then the output should shift by n sub d. And that should be true for any shift. What this means is the transformation doesn't change over time. In the word problem, it means if I hit the desk today and it makes a sound, if I hit it tomorrow, it should make the same sound. Stability, another important property. Bounded input, bounded output stability. So that means that if the input is bounded for all time or all n, and the upside down A method is a math symbol meaning for all, then the output must be bounded by some bound. It doesn't have to be the same, some finite number for all n. And so one of the examples that we had was the accumulator, where we saw that if we put in the unit step, the output of the accumulator, of course, was a ramp that just kept increasing and became unbounded. And so that's a nice example with a bounded input, the unit step, and the output being unbounded. So we see that linear and time invariance are just very common sense things. And so it's important to consider these general transformations in the particular case of a linear and time invariant system. So we only impose those 2 requirements. The second thing is we're going to view x of n as the sum of a bunch of delta functions. And so if we have some x of n, let us say is 3, 2, 2, We can view that as the sum of three delta functions at each of the delays, and then this one's multiplied by 3, this one's multiplied by 2, this one's multiplied by 2. So this is the multiplier, and these are the delay delta functions. So with this concept, now we're going to operate and find the output of x of n, which is the transformation of x of n, but it's now the transformation of x of n broken up into these pieces. By linearity, we know that if I have an input x1, it produces an output y1, but if I have an input ax1, its output will be ay1. And so using that principle, the transformation of x times delta, the x acts as a multiplier, it acts like the a. And so I can pull the x out front, and now I just have the transformation of the delta function. So that transformation of the delta function is just whatever the output y is for the input x being a delta function. And so, of course, we would call that the impulse response. And so that's just h of n. And if the system is time invariant, of course, it doesn't matter how long we delay the impulse. It produces the same shape, the same h of n, or makes the same sound tomorrow as it did today. And so the shape h of n is unchanged, no matter how much I delay the delta function. And so by linearity and by time invariance, we arrive at this summation, which is convolution. And so this is convolution for a discrete time system. So the output is the summation of the inputs x multiplied by h of n minus k. This resembles, of course, continuous time convolution. If you recall, y of t for continuous time system equals the integral of x of alpha h of t minus alpha d alpha. And so this has the very same form. The integration is done over alpha, so I have x of alpha and a minus alpha here. The summation is done over k, and so I have x of k, and I have a k being subtracted inside of h. And finally, the answer is y of t, and we see that t is the leading term in h. And so that corresponds to the n for y of n being the answer, and the n is the leading term in h. And so it has the same form as convolution in time, but now instead of integration, of course, we have summation for discrete time. As you work these out for the first few times, I think it's very important to write the summation out. It's quite easy to assume that you know what the summation is, but it would be very good practice to actually write out the summation the first few times you may do this. Of course, linear and time invariant systems are most of the systems you encounter, and convolution is the process by which you can compute the output of a system based on the input and its impulse response. And so it serves a central role in discrete time systems, the convolution sum, as it does in continuous time. And again, the form is very similar, except we have an integration, we have a summation instead of integration. So it looks a lot like the continuous time case. One last detail, the convolution of h with x is the same with x convolve h. So we can interchange the order, and that means I can replace the x by h and swap them in the summation. This is extremely important result. It's as important, right, in discrete time systems as convolution is in continuous time systems. So one way to do convolutions, perhaps the most insightful way, is to view the convolution sum, where we view the x of k's as weights, and the h of n minus k's is just delayed versions of the impulse response. So for example, if we have a input signal here, which is a 3, 3, 3, 1, and we want to convolve that with an impulse response, it's a 2, 1, 0, 0, 0. We could add a 0 here at the end. And just as a shorthand notation, again, these are infinitely long sequences, so I'm assuming that it's 0 to the left and it's 0 beyond. And so if we view these as weights and just change values of k, the first value, let's say, is x of 0, h of n, when k equals 0. So this first case is k equals 0. In that case, the weight is a 3, because x of 0 is a 3, and it multiplies the impulse response, which is 2, 1, so I get a 6, 3 unshifted. At k equals 1, I have x of 1 times h of n minus 1, and so now I have weight is 3 again, but now it's shifted 1 to the right, so I have a 6 and a 3 again. X of 2 times shift 1 more to the right, x2 is a 3 again, and so I get a 6, 3 once again. And finally, x3. Now x3 is a 1, but it multiplies again shifted, so I get a 2, 1 for this last shift. If I went to x4, I don't need to worry, because the weights are 0 beyond that last point. And so I've completed with all my non-zero shifts and weights. Then finally, the last thing I have to do is the summation. So I add all these functions together, and so I get 6 in this column, I get a 9 in this column, I get a 9 with this 6 plus 3. Here I get a 3 plus 2, so I get a 5, and finally I just have a 1 at the trailing. And so the convolution is 69951. There's a second way to do this, and so we can use this bracket notation. And so I just do the same thing, and so my first weight is 3, and that multiplies this h of n, so I get a 6, 3. The second value of x of n multiplies a shifted version, so it multiplies this 2, 1 shifted 1 to the right, so I get a 6, 3 shifted 1 to the right. Shift again, 6, 3, and then finally the last weight, 1, produces a 2, 1, and if I add these together, I get a 6 for the first, a 9 for the second, so I get the same answers using this shorthand notation. So convolution's pretty straightforward. If we just view the convolution sum, first values are weight, and the second values are delayed versions of the impulse response multiplied by that weight. And so it's easy to do it either graphically. I think graphically gives you kind of an insight to what's happening. And then once you have that insight, the bracket notation is probably easier. So next, let's discuss property transform. First property is Z transform. It's linear. So if I have ax1 of n plus bx2 of n, the Z transform is ax1 of z plus bx2 of z. And that's easy to show just by substituting in the definition of the Z transform. It follows by the property of the linearity of the summation formula. Shift property, another important property. Here again, we're doing two-sided Z transforms. And so the Z transform of a sequence shifted by n0, just plug it into the definition of the Z transform. Here we'll just use change of variable, so we replace n minus n0 by alpha. And so now the exponent becomes alpha plus n0. And I can split that exponent, bring the z to the minus n0 out front, and then all I have to do is recognize that this is a z transform. The only difference is I have a different variable. I could replace the alphas by n's again, and note that I have the z transform. So the z transform of the shifted sequence becomes z to the minus n0 x of z. And so this forms a transform pair. This is the shift property of z transform. We'll mention later on, for the one-sided z transform, it's a little more complicated. This is true if I'm shifting to the right, but I have some problems when I shift to the left because the one-sided z transform assumes causal sequences, and I may be shifting non-zero data into a non-causal position. And so this is one of the reasons to use the two-sided z transform. I don't have to worry about that in the shift property. So in our block diagrams, we have used a shift of a sequence, and so we just put it through a delay. So x of n became x of n minus 1 through a delay. Now we can use just z to the minus 1 for a delay of 1, and that's typically how a delay is written in a digital circuit diagram. And so here, if we drew the z transform of the input would be x of z, the output would be z to the minus 1 x of z, which would correspond to the z transform of x of n minus 1. And so just taking z transforms across this block diagram, the delay becomes z to the minus 1. And so typically, delays are drawn as z to the minus 1 in digital signal processing block diagrams. So I mentioned that the one-sided transform is a little more complicated. I'll go through that detail here for a moment because quite commonly in controls textbooks, the one-sided transform is used, although that's less common to be seen in digital signal processing. So again, one-sided transform presumes all signals are causal. The summation, of course, goes from 0 to infinity. And so a left shift becomes a problem. So the shift property for the one-sided z transform, if we look at a shift by n1 to the left, we see that this transform has, again, by change of variable technique, we can pull out a factor of z to the n1 up front and replace the variable again so it's clear that this is the z transform of x of n. But we have to subtract off terms that would be non-causal, and so we have to subtract x of n times z to the minus n for values of 0 to the n1 minus 1. And so again, this first term gives us the z transform, z to the n1 power times x of z. But the adjustment here to remove the left half of the sequence is we have to subtract off values from 0 to n1 minus 1 times z to the minus n, again, times z to the n1. So kind of summarizing, if I have a shift to the right, again, n0 assumed greater than or equal to 0, then it has the same property as the two-sided z transform. However, if I shift to the left, I have to tend to the fact that I'm adding terms that do not exist in the normal definition of the Z transform because it's assuming causal sequences. So for a left shift property, I have to subtract off those terms that are associated with the left shifted portion of the sequence. And so for a one-sided Z transform, the left shifted data disappears to the left of N0, so to speak, to retain causality in the solution. Convolution property of two-sided Z transform, again, another important property. The Z transform of X convolve H, so we can plug in the definition of convolution. And again, illustrating the use of the techniques to prove these properties. So we're going to interchange the order of summations. So the sum of K is going to come up front, and we'll put the sum of N on the inside. And we can see right away that this is the Z transform of a delayed version of H. And so we can use the delay property. That's just Z to the minus K H of Z. And the X of K summation is still left up front. Of course, H of Z is not no function of K, so we can pull it out front and recognize this is X of Z. And so simply the Z transform of the convolution is the product to the two Z transforms. Of course, very important property, very similar to what we see in Laplace and Fourier transform. One detail is the region of convergence. Typically is the intersection of the two regions of convergence. So of course, if an area where one function is finite and the second function is finite, the pair should be finite. And so it's the intersection. There can be unusual cases where there might be a pole zero cancellation. Those are best to be very cautious of, even if you see that. And so the safest bet is to assume the region of convergence is the intersection of the two. Just as in Fourier transform, we can take the Z transform across the block diagram. So X of N gives X of Z, H of N gives H of Z, Y of N gives Y of Z, and the convolution gives the product of the two Z transforms. And so this kind of is another illustration of the notion that the time domain view of the signal is one language, and the Z domain description of the signals is, let's say, another language. There are just two languages describing some process that's being described in an engineering sense. And so in a way, the Z domain and the time domain are just two tools in an engineering sense that allow us to predict what the system will do, whether the system's stable, and so forth. So the two-sided transform is very easy because of the simplicity of the shift property. If you recall, the one-sided Z transform, of course, presumes all signals are causal. And so the shift property becomes more complicated. And so we have to be a bit more careful with the shift property. And so taking the Z transform, of course, if we're using one-sided Z transforms, both indices sum over 0. And we can do the same thing, interchange orders of summation, and see that the inner sequence, of course, starts at 0. And so this is a shift right property. And so the shift is indeed Z to the minus K H of Z. And then once we have H of Z, we can bring it to the front. And notice that the Z transform also is proper for x of say k z to the minus k. And so we have x of z, h of z. And so we see that the one-sided Z transform has a bit simpler convolution than the shift property because we noticed that in both cases the summation started at 0, and so we didn't have the difficulty of a left shift. So the Z transform of convolution is just x of z, h of z, but the presumption here is that both h of n and x of n were causal. And so the one-sided Z transform of causal sequence X and causal sequence H is the same as the two-sided transform as long as the sequences are both causal. And so for the typical case that we consider in most control system applications where the functions are causal, the one-sided and two-sided Z transform would give the same result. Perhaps a bit less used is the modulation property. And so if I multiply a sequence by some complex value, z0 to the nth power, its Z transform is x of z over z0. And so it's pretty straightforward to show this. I'll let you work through these details. The particular case of interest is when that z0 is a complex exponential, e to the j theta or e to the j omega 0, because the angle on the unit circle indicates frequency in the z plane. And so that would mean that x of z over z0 becomes x of z over e to the j omega 0, which of course, if I wrote this in polar coordinates, would be r e to the j omega, which is z, times e to the minus j omega 0, which, because bringing the j omega 0 up to the numerator, which finally I can merge the exponents and becomes r e to the j omega minus omega 0. And so what that means is that the Z transform becomes rotated in the Z plane. So the entire Z transform becomes rotated by omega 0 in the Z plane. And so this rotation in the Z plane would correspond to a frequency shift, because recall that the unit circle is a frequency axis. And so if you induce a frequency shift along the circular axis for the Fourier transform, that would correspond to a rotation. And so shifting the frequency by pi over 2 would be moving the DC value from 1 to j. And that would correspond, if we were looking at frequency shift, let's say a function that repeated at 0 and 2 pi, that would be shifting the frequency response by the value omega 0. And so that can be useful in operations where you need a frequency shift. Another property of Z transform is the system is bivostable if the region of convergence includes the unit circle. And so this is very important property to be observed in the Z plane. It's similar to the Laplace plane. If the region of convergence included the j omega axis, then the system was stable for the one-sided Laplace. For the Z transform, we already saw an example where we had a to the n u of n, and we saw that the pole was located inside the unit circle. The region of convergence was an exterior region. And so this was an early example of a stable, well-behaved exponential sequence that included the unit circle. In the time domain, we can also note that system is bounded input bounded stable if the impulse, some of the magnitude of the impulse responses magnitudes is bounded. To see that, we can see that the convolution, so if this is my output, is just the convolution. That's less than or equal to some bound on x, that's the largest absolute value of x, times the magnitude of the impulse responses. And just a simple argument, if the impulse responses are positive and minus, they could add and subtract from each other, but if you take the absolute values, they only continue to add. And so this must be greater than the original convolution sum. And if this is less than or equal to infinity, the output is bounded. And so this will be true. We can pull the b sub x outside. That's just the largest value of x. And so this must say that the sum of the absolute values of the impulse response are bounded. Then the sequence is bibostable. And so these can be infinite sums. And so simple example would be 1/2 to the n u of n. So that'd be 1, 1/2, 1/4. And we know that the sum from 0 to infinity of 1/2 to the nth power equals 1 over 1 minus 1/2 equals 2. And so that sequence, that exponential sequence, 1, 1/2, 1/4, 1/8, is bibostable. And we recall that sequence looks a lot like the impulse response of an RC filter, which of course is a bibostable circuit whose output is an exponential decay. Its impulse response is an exponential decay. Final properties, initial and final values. X of 0 is the limit as z goes to infinity for causal x of n. The final value at x equals infinity is the limit as z goes to 1, 1 minus z to the minus 1 x of z for causal x of n, or right-sided x of n. So